I'm Jonathan Ellis, and I'm going to be speaking about big data for cloud applications. And to put that in context, I see databases in general as split across two axes. We have at the bottom here, we have the analytical category, and then at the top we have operational. And then you can kind of split that horizontally as well between the legacy side and the traditional client-server databases from the 90s, and then you have the post-relational big data systems. So in the operational category, you have Oracle, you have SQL Server. In the analytical category, you have Netezza, you have Teradata, and then moving around counterclockwise, you have Cloudera, Hortonworks, MapR in the analytical big data category, and Cassandra, MongoDB in the operational big data category. So in general, you can categorize these big data analytical systems. These are what you're going to build your data lakes with. And then the operational big data systems, that's where you're going to build your cloud applications. So what are cloud applications? Cloud applications are where you have a multi-tenant system as opposed to your legacy databases are generally, I'm going to have one database deployed at UBS and one database deployed at British Gas. But those are only for the employees of those respective companies. And a cloud application is one where you're selling this to an entire country or an entire world. Your Spotify and all of these multi-tenant distributed applications that are having hundreds of thousands and millions of users, and that's what operational big data is about driving these new applications. So there's three categories of requirements for these cloud applications. They need to be always on, they need to be able to scale, and they need to be high performance. And I'm going to talk about each of these in turn. So starting with Web 1.0 in the late 90s, we've had an expectation that cloud applications are going to be always on. When I go to Google, I'm always going to get the Google search bar. I'm not going to get a page that says, we're down for maintenance, come back tomorrow at 6 a.m. That took another step forward with Web 2.0 and the rise of mobile applications 10 years ago when the iPhone was introduced. Now you have companies that are developing mobile first, and that's a new expectation that when I pull out my phone and I bring up your application, I'm always going to be able to use it. It's always going to be available. And so to build that, we needed a new paradigm in our infrastructure, because the classic client-server design, this worked fine in the 90s when I have a single company's worth of data on my server, and it's okay to take downtime for expected maintenance. But in today's world, it doesn't work. And so what you see is, or what you saw initially was people tried to take this client-server paradigm and extend it to make it fit this new world of cloud applications. And so the first thing that they'd have to do is, as their data no longer fit on a single server, was partition that data across a bunch of different shards and say, okay, these users' data belongs on this machine, and these other users' data fit on this machine, and so we partition that out. And then we add a couple slaves for failover, because if I lose, I don't want to have catastrophic data loss if a single machine goes down, so I'm going to have that replication for failover. Maybe I'll also serve reads directly from those replicas to spread the read workload around my cluster. And then I'll need to have some service in front that says, okay, you've got your data set partitioned, but now when I come in and I say I want to find the records for Jonathan Ellis, I don't know just from that that name, where to find which partition those records are going to be on. So I need to have some kind of routing service that tells me where to find the records that I'm looking for. And then finally, now my client, when I have an update, the client can come in and say, okay, routing service, where does this data live? I'll go and talk to the master for that partition, and then the master will propagate it to the replicas. And so this is where the industry was, at the beginning of the new century, where we'd taken this classic architecture and kind of expanded it a little at a time to be able to handle the demands of first-generation cloud applications. But there's a couple problems with this in terms of the requirement that I articulated that we want to provide an always-on experience. So the first of those problems is by design, I'm engineering for failure, for fault tolerance here. So if I lose this master, it's not the end of the world. But because it is a master-based system, until I fail over to a new master and elect that new master, I have downtime. So I can't handle updates. If I have a strict consistency requirement, I can't even serve reads until I elect that new master. So that's kind of built into the architecture, and even if the architecture works perfectly, I do have that window of downtime when failures happen. But there's actually more subtle problems with this. For instance, if I'm back to my cluster here and all the machines are working, but a switch fails on the network, and now some of my machines can talk to each other, and I've represented that in the lower left here. Some of them can talk to each other, but they can't see the rest of the cluster. And meanwhile, the machines on the upper right can talk to each other, but not to the machines in the lower left. And so I've represented that network partition with that dashed line through the slide here. And so what will happen if you're not careful is that the upper right part will see those. It won't be able to talk to those machines in the lower left and say, okay, those machines have failed, or I can't talk to them, which is the same thing in a distributed system. So I'm going to elect new masters. Meanwhile, the machines in the lower left saying, well, I was the master, and I'm still alive, therefore I'm still the master. And so you have a system now where there's multiple masters for those two partitions that were affected. And so this is, and yes, there are ways you can mitigate this, but this does happen in real-world systems. So this is Armin Ronecker. He gave a talk a couple years ago about how basically this exact scenario happened in his MongoDB cluster. So the architecture I've given you with masters and slaves and partitions and a routing service is basically a simplified version of the MongoDB architecture. And so this is a real problem that happens in real systems. That's how MongoDB got the industry-leading reputation it has today. But on the other hand, if you're going to start from first principles and say, how am I going to design a system that meets this requirement for fault tolerance, for being always on, that doesn't need to worry about network partitions, that doesn't need special heroic failovers with downtime if a master goes down, how would I build such a system? And that's what the architects of Cassandra, that's the approach they took to solving this problem. And so what we ended up with was a system where any node in the cluster knows how to route a request to the machines that own a piece of data. And so we've gotten rid of the need for a routing layer because it's built into the cluster. It's part of the replication design. And then there are no masters either in this system. So I've represented a piece of data, this partition 1 in yellow, and that can be scattered around the cluster, and a second partition could share some of those same replicas with partition 1. And critically, there's no master, there's no slaves, but everyone is equal in this distributed system. And so if the machine on the left here fails, that's all right. We can still serve requests from the 2 remaining replicas that are up without needing to take explicit failover actions and without having any downtime. One of the great petri dishes for proving a system's resilience is Amazon Web Services, because this is a very big set of infrastructure that does experience outages. And so if you can tolerate the outages in Amazon's public cloud, then you can probably tolerate outages anywhere. And I say this not because Amazon has challenges here, but rather that challenges are inherent to providing infrastructure at scale. And so my point is not that Amazon is bad at this, but rather that Amazon is the best at this, and even the best in the world are still going to have outages. And so if you look at the AWS outages, roughly once a year, most of these were in the American US East Data Center. The most recent one was actually in Sydney. But you're going to have to deal with outages and machines failing and networks failing. And so looking at Cassandra in the AWS infrastructure, we've been able to demonstrate that kind of resilience. So Netflix went on the record in terms of their 214 Cassandra nodes rebooted without warning during what some people called the reboot apocalypse of 2014. And during that, of those 200 nodes that got rebooted, 10% of those didn't come back at all. But throughout all that disruption, Cassandra was able to take that in stride, and they saw no downtime in their application. The next requirement for building cloud applications is the ability to scale. And so Cassandra has demonstrated that ability at the largest use cases in the industry. This is a slide from Apple's Cassandra Summit presentation. They have 75,000 nodes of Cassandra with tens of petabytes of data on that. And so I do like to be able to point to this and say, we can scale as large as you need, even if you're Apple. But I think it's more interesting maybe to talk about a user that's more close to the average. So there's a startup called ProtectWise, and they started off in DataStax's startup program, which is where you get to use DataStax Enterprise for free as a small growing company. They started with 3 nodes in 2013 and grew to 300 2 years later. And so Cassandra gives you that ability to grow incrementally as your needs and as your user base grows, and grow with you, and up to and including those largest needs in the industry. Another important factor in scaling a cloud application is the ability to go across multiple data centers and multiple regions. And so I've illustrated that here with a cluster that spans a London and a New York data center. And you'll note that New York has 8 nodes and London has 5. And I've made that asymmetric on purpose because we can do not only symmetrical replication, but also it can be very fine-grained. And I can say, I want 3 replicas of this data in New York, but I only need 1 in London to do analytics against it. And so you can do that kind of fine-grained configuration of how you want your data replicated across those data centers. And it can be live in both data centers. So this isn't just disaster recovery where London is a cold failover target, but rather I can be processing new transactions and updates in both of these locations concurrently, and they get replicated asynchronously and performantly. This is actually critical to providing the kinds of uptime that I talked about with the Amazon Web Services failures. So even if you lose an entire region, even if you lose the US East region, if your Cassandra cluster spans from US East to London, then losing US East won't be critical, because the way you configure this is you want to take advantage of having both of those regions live and able to handle active transactions. When the cluster is healthy and everyone is alive, you want to take advantage of that by sending users to the data center that's closest to them, and they get better response times and better performance from that. But if one of those regions goes down, then you can just redirect that traffic that would have gone to the New York data center. You can send it to the London data center, and everything keeps working. You don't need any explicit failover events at that level either. So the scale story and the availability story, they go together, because having this asynchronously replicated across multiple geographically separate regions is critical for handling that category of outage that affects an entire data center's worth of infrastructure. Finally, I want to talk a little bit about performance and how do you build a database for cloud applications in a way that's going to meet the performance needs of today's industry. So one of the first ways that people started off doing this, I showed you at the beginning that one way was they started off with taking databases like Oracle and partitioning those out manually. The second way that people started off trying to do this was taking a distributed file system like HDFS and trying to build a database on top of that and saying, well, the file system takes care of partitioning for me, and so that's going to simplify building my database on top. And there's some truth to that. There's a kind of architectural elegance to saying, okay, all my database needs to know is that there's a global file system that takes care of partitioning that for me, and so my database itself doesn't need to do that. But here's a problem with that approach, which is that if you look at the HDFS architecture, for instance, you have the name node that's kind of the metadata service and knows which data nodes contain which files. So this is actually kind of like the routing service node in my earlier diagram. And then you have each of those data nodes that replicates the files. The problem is that HDFS thinks in terms of 64 megabyte chunks of data. And so if you're using Cloudera's distribution, I believe they use 128 megabyte chunks. But if you're building a database on top of this and you want to read a 4 kilobyte record, and the underlying file system is amplifying that to a 64 megabyte read, then you're leaving a lot of performance on the table. And so one of the things that you want to look at when you're evaluating databases and database performance is there's these twin concepts of write amplification and read amplification. So if I write a 1 kilobyte or a 4 kilobyte record, how many kilobytes or megabytes does that turn into in the database that actually get written to disk or sent across the network? And then on the other hand, if I go and I want to read that record, how many bytes need to be pulled from disk to read that? And so where I'm going with this is my point is not that HDFS is a bad design, but that it's a design for these analytical systems where I want to scan through vast amounts of data and compute out business intelligence from that. And so, in the automotive analogy, it's an 18-wheeler and not a sports car. And so it's designed for that, and it's good at that. But when you have a cloud application that wants to do lots of small requests, then that's a bad fit for something like HDFS. This is Murat Demirbas. He's a professor at SUNY Buffalo. That stands for State University of New York in the East Coast of America. And he looked at an analysis called Simple Testing Can Prevent Most Critical Failures, where the authors of this paper looked at Cassandra and they looked at HBase, and they compared the failure modes of those two systems. And they categorized the failures as either a routine or catastrophic. And a catastrophic failure meant that either the system was down or that it lost data. And so Dr. Demirbas summarized this as, it seems like HBase is very buggy where 50% of sampled failures are catastrophic. And that's not because the engineers who work on HBase are dumb, but because they've got this very complex system where they're starting with HDFS and layering on an HMaster and tablet servers on top of that, and you have to deal with failover and migrating data to a new master when one goes down. And so there's a lot of things that can go wrong in that scenario. And by contrast, the Cassandra architecture of it's a fully distributed system where every replica is co-equal with every other one, it's much simpler and much easier to iron out that kind of failure. On the performance side, what Cassandra's architecture allows us to do is within each node on the ring, each node is responsible for managing its data locally. And so we can use the tools that the operating system gives us, like mmap and fadvise, to control how we're pulling data into memory from the file system. And when I go and I do a 4 kilobyte read, I'm going to do some read ahead, but I'm not going to pull 64 megabytes in to answer that. That's going to kill my random access performance if I do that. And then we build on top of those constructs. We have our own commit log on a per replica basis. We store the data in a log structured engine called SS tables, and then we build higher level constructs on top of those. And so we start with as close to the metal as we can, and we build up from there to get high performance. And so DataStax hired a company called Endpoint to benchmark some common NoSQL systems. So it's a little bit small on the screen, but at the bottom you've got Cassandra in blue, Couchbase in red, HBase in yellow, MongoDB in purple. And so we've got 4 different workloads. This is write mostly, it's 90% writes. Read mostly, 90% reads. Balanced is 50% writes, 50% reads. And mixed operational and analytics. And so what this last one means is we're recognizing that it's not going to be pure random access small queries, but you are going to want to ask some of those analytical questions of the system and ask, if I'm an e-commerce site, compute when users bought this product, what other products did they also buy? I want to be able to make some recommendations to my users. And that's more of an analytical query, and so you want to be able to support those as well. And so this, my contention is that this performance advantage comes from the architectural decisions that I've described earlier, to build it as a fully distributed system where the master is not a bottleneck or a fault point, and to be able to leverage the local performance that you can gain from managing storage locally instead of as a DFS abstraction layer. So of the, I've mentioned these three categories of being always on, being able to scale, and being high performance as being critical for cloud applications. Let me just briefly mention kind of a third-party analysis, so it's not just me bringing this to you. So Gartner released a report last month called Critical Capabilities for Operational Database Management Systems. And so they gave four categories of those critical capabilities that they considered important. And those were traditional transactions, which are the kind of green screen terminal to a mainframe, begin transaction, rollback or commit. And then we have distributed variable data, lightweight events and operations, and hybrid transaction and analytics. So the first one of those, the traditional transactions, is not super relevant to cloud applications, but here's where they ranked the systems for these other three. So distributed variable data, DataStax is at the top, and we've got some pretty heavyweight competition on this slide, and so I think I'm very proud that we were able to be recognized in that group. Lightweight events and observations, DataStax is also at the top here. So again, these lots of these point operations, hundreds of thousands of requests per second of read this row or write that row, very, very good at this category. Now, just so that I'm not blowing smoke here, I'll show you this one, the HTAP one, hybrid transactional and operational. DataStax is not the top one, but we are in the top 10. And so this is a place where, as I showed you in one of our performance charts, we do recognize that it's important to be able to do analytical queries against your operational data. And so if you'd like to learn more about what we're doing with any of these categories or with those keys to cloud applications on big data databases, please stop by our booth. We're going to have some lightning talks during the day, today and tomorrow, that are going to go into more detail on some of these subcategories and go a little more into the weeds on how do you actually go about building an application on DataStax Enterprise. So thanks for your time. We don't have time for questions right now, but feel free to catch me at the booth, and I'll be happy to take questions there. Thank you.